So, a major problem with growing tissue in laboratory or cells is how nutrients are transported. Some places will get too much oxygen, some places too little oxygen, and all these other nutrients. And in your body, you have a very, very complex transport system. People talk about your heart, your lungs, but beyond that, you have blood vessels that are adaptable. When you need more blood to a part of your body, they grow with your body and work to give more blood to certain parts of the body. You don't have that. You have your lymph system, which is a kind of a separate system that transports more outraised and more also white blood cells, roughly. Um, then you have like other systems for transport. But not only do you have these local blood vessels that grow, they can also disappear if there's too much stuff going to a certain area. You have local deposits of fats or storage, so things can locally get stored for when they really are needed, which adds complexity. You have different sized vessels that can, bigger vessels can transport a lot more, but they can't get absorbed as quickly. And that helps make an even better distribution than a bunch of small vessels, which stuff through small vessels cannot transport as fast because there's more friction through the surface of the walls, or might lose stuff too quickly, the nutrients. Then beyond all this stuff and different control the porosity stuff, you also have extra pumps in your body that's not your heart to transport all these nutrients. These includes your major arteries have muscles that help pump the blood, and especially important in your legs and stuff to keep circulation going. Actually, movement helps transport nutrients throughout your body. That's why when you're walking, it helps with digestion. It helps with certain positions, help with breathing, and all these the vibrations from your heart actually help also stop blood clotting and transport stuff. And everything is going together. So it's a lot more complicated than people simply make it sound like. So now that you understand the complexity of this, it's something when you're growing a lone tissue like a muscle, it can be very hard. Because not only would you have to grow the structure, but you have to grow hearts and all these complex controls. But it could also be a problem if you're just trying to grow a very dense tissue, very dense bats of non-tissues. There's like a bunch of bacteria or a bunch of human cells that are just all close together and all sucking out the nutrients because they can, if you just put on oxygen on the top, enough oxygen on top, locally the oxygen might not reach the bottom, so locally there might not be enough oxygen, and top there might be too much. Or 1,000 other nutrients. So I've come up with maybe a simple idea around this whole thing that could be made super complex. So imagine you have a container. I'm just drawing a square. And I know everything is not centered perfectly. And each of these squares, you have these little blue-green squares that there's 9 of them I drew, but they could be many of them. And each of them can shake and have a vibration. Now, what they can do is, with the vibrations, is they can help move nutrients. If you vibrate from one point, the nutrients get pushed away from the point you're vibrating. And if you have multiple ones, you can control it. If you have them all along, let's say the top side vibrating, then it puts everything from the top side to the bottom side, or vice versa. You can make complex patterns like circles where the top moves it somewhat, then the side moves it somewhat, and the bottom moves it somewhat, and then another side, and it makes a circular pattern as it occurs by varying different things. You can use these vibrations also to help prevent stuff from clogging up, and not only prevent stuff from clogging up, you can actually, if you have really strong vibrations, you can break stuff up in it, while weak vibrations will not cause that breakup. And to give you an idea about how, and the more ones you have on it, the higher resolution you can get. And you can get already very, very high resolution, as you can illustrate, if you have a bunch of little sensors, as you can illustrate with like ultrasound, the reverse, where you sound to detect stuff, it can be very, very high resolution in 3D space, such a small probe. So if you could have a couple of these ones that are millimeters, you could get millimeter down resolution of where you're moving stuff. You can even use different size, bigger waves to move bigger things and smaller waves to move smaller things in a controllable manner, and use different wave spectrums to sort stuff by its size or molecular weight if you really want to get fancy. So a huge potential there. Now, once you move all this stuff, there's another big question going on, and that is, how do you make sure that everything is moving in the right place? Well, there's a way you can get pretty high resolution, and that is, if you want to measure how much the wave is interacting in place, how much it's going up and down. Well, how much it goes up and down, a wave goes up and down, or how much it compresses or decompresses, changes the absorptivity pretty linearly. So if it gets compressed twice as much, it absorbs about twice as much light. Decompressed, it absorbs about half. So a simple camera sensor could detect it, and you would need only a resolution of about 4x4 pixels per sound sensor. And these sound sensors, and when you have like resolution in the megapixels, where it's thousands by thousands or more, this is more than enough. That means you could easily use a standard camera to detect it for, literally, you could detect it for a meter by meter cube easily, just with a standard camera, but you need one on each side. Then you would have to design a software to look at all this data. Now, the software would be one of the biggest challenges, and the software I propose would first, there's kind of 3 parameters, and this is why I choose 4x4. And you'll see in a second why for each of these ones. One is how much the wave weakens at a certain point, would tell you how much powerful the wave you need to do, or how you have to judge a wave. That's an important parameter. I wish though, I'm going to make my next line a little bigger. The second really important parameter, and these two are about the same. I would say actually the second is a little more important, so we can switch the order if you really want to, is speed of the wave through that material. And then the third one, besides weakened speed, is scatter. Now, I'm going to go through all of these different things, and I'm going to explain to you how they kind of affect. So when the scattering is actually about how much different the speed is between point A and point B, and you can measure it. And anything with scattering, if you have enough points that you're measuring, you can always kind of approximate it with adding more points, but making your model have more points, and then just looking at scattering, weaken, and speed. Because speed, whenever something goes from a slower medium to a faster medium, it bends a certain way. It bends in. When it goes from a faster medium to a slower medium, it bends out, because it kind of curves in. The leading edge hits it, slows down, and the other edge catches up and turns away. Weakening something can do the same thing. Weakening it is kind of like slowing down the speed in many ways. So it bends it in a similar way. There are other things that can happen to scatter it. But first, what we would do is we would make a model, look at the speed, which is the biggest factor. Then we'll try to add on weakening the model. And it's doing this successively. and it has a way of doing it with just doing slight corrections that are not big leaps of phase. Then it would, in the next correction, it would add scattering. Now, if you have enough points, you can also add the other component, directionality. And directionality is can be modeled because directionality has a, if you have enough small points, you can actually make this whole thing add like a directional mirror by making it more permeable one way. So it's increasing values of scattering and speed in one way more than the other way, which can give it, or along a certain direction, which can kind of actually give it directionality. So instead of actually modeling a fourth parameter, you just model more points in your model. You can also give it, to some extent, the ability to detect different waves. And if you want to do that, you're going to take your sensors, your 4x4 sensors now, and then you can make a model that has, with the frequencies that you want, it splits it up into regions that are about half the size of the frequencies you want, or 1/4 if you want to do some overkill. If you're vibrating up to millimeter, that will be millimeters, so on and so on. And that can give you frequency dependence, so that it bends stuff differently depending on the frequency. All this is pretty fast calculations, and our computers are getting a lot faster. But if you want to do it on a millimeter scale, this is so fast, and we'll get rid of error so much. But I have a way of making this even faster and more accurate. And that would be, we take these steps 1, 2, 3. We first do 1. Then we have a predictive model that predicts how 1 will change, that predicts how we will change it in the next step. And this will be a neural network. And this, then it'll predict from step 3, from step 2, how step 3 will change it. But this is using a neural network that has machine learning, and it actually doesn't know whether this is on step 1, 2, or 3. And then, so that would, what that would secretly do is it will train 1 to take into account 2 and 3 in the next step, in a way, because it is correcting for both 2 and 3, or 2 will correct for both 1 and 3, and also correct a little bit for itself. So it's looking at kind of future correction because it doesn't know what the next step is correcting for, and kind of bring it to a medium. This step would be made less strong than other steps so it doesn't overtake them for a more big thing. But this will also allow for more of a global factor, because each step only really looks, with the 1, 2, and 3, what it's doing is it first looks only at the neighborhood with these models. So square 1 is only going to make predictions based on like this square in the middle here will only look at its neighbors, and so on and so on. Then you do it many times, and because one neighbor affects the neighbor next to it, affects the neighbor next to it, if you do it in 2 steps, something two away will affect it, and so on and so on. And this can be a pretty good approximation, but this will actually let it see it farther beyond, because it's looking at stuff like a couple steps ahead, where stuff farther away has already affected this, allowing for even faster that way, and kind of mix up stuff. Well, thank you for listening. Please like and subscribe. It really helps the channel out. I'm trying to reach 1,000 subscribers in a year and 4,000 watch hours, which is really, really hard. But with your help, I think I can do it. Also, if you have any ideas for future videos, comments, or suggestions, please leave in the comment section below. Thank you very much again. Goodbye.